Great. Okay, it starts.
Oh, this is way better than the one I made.
Okay.
Mine
It's
was
just
just like
words.
retyping things on the paper and then in parentheses writing like my version of it in my head.
Oh god,
That sounds great.
This is supposed
that is
to
so
be-
janky, but we got it. Okay.
Okay, cool.
Before to start, the idea is you present everything and then we discuss, or we discuss while you are presenting.
You can do either.
Can we ask
I like
you
questions
questions?
ask it during any final mistake. It's kind of overlap. So.
So I might just forget. I'd have to write it down.
Between 2D. Oh, they are sandwiched. Look, you made the word sandwich.
That was intentional. Okay, so this is paper 5, the nucleation growth of WSe2. So I made this presentation kind of as my thoughts on the paper, because I do molecular beam epitaxy and I worked on WTE2 in undergrad, very similar material. So this is just kind of what I would say to give background on the paper and like why did they do this, not necessarily what they did because you can read the paper. So I focused more on. You good?
Yeah, we're good.
Yeah, so I focused more on like why they did things and not necessarily the detail of the growth mechanisms, because that's pretty well outlined in the paper, I felt like. So first of all, what is a transition middle dichalcogenide? I can still say that, which is what WSe2 is. So it takes a transition metal and puts 2 chalcogens with it. So chalcogens are sulfur, selenium, tellurium. So there's a whole bunch of these. It's just a family of this type of compound, and they are 2D materials. So they are much larger in plane than they are out of plane. And the whole reason why these are so interesting is because they discovered graphene and they're like, whoa, 2D materials, there's no dangling bonds, it's super conductive and stuff, that's really cool. But what if we had a semiconducting 2D material? So that's kind of where the motivation of these guys came from. And they have a bunch of different properties like edge effects, and some are superconductive, a bunch of band gap things.
What's an edge effect?
The effects that happen around the edges.
Okay.
Very much like, okay, it might conduct here and not in the middle, sort of thing. Yeah.
I've heard dangling bonds mentioned in other papers, and I'm curious like what the
It was like a taxi paper with the.
yeah
silicon.
what because I didn't do this paper, but I think I did another like the epitaxy one. What's like I guess the cons of like a dangling bond in some of these
It'll
applications?
oxidize really, really fast, or like just attach itself to other things.
Okay.
And so the absence of dangling bonds is like the picture in the top right there, where there's nothing for it to
Okay.
look like physically. There's nothing where it
But
can
it's-
attach onto it.
Like you have a surface and you have a free valence electron over the surface, and this free valence electron over the surface can react with something else.
Yeah.
It can create a bond between
Yeah.
surfaces.
But
Yeah,
two
usually
is
on the
nice.
surface.
Yeah.
Yeah,
Mhm.
because like the bulk ones, they can bond, but the surface, there's no connection. So
Yeah.
it's just
Not
yeah.
to say there isn't any weird surface effects that can happen,
Mhm.
but there's just the bonding thing doesn't want to happen as much. Therefore, there are van der Waals bonds instead, and that's how these layers are bonded together.
So they do not have dangling bonds, or do they? Some of them do.
2D materials
Good,
do
okay,
not have.
okay.
That's kind of the definition of 2D material. They have van der Waals bonds though,
Mm-hmm. Yeah.
so not like a normal covalent type of bond or anything.
Okay.
So these materials are made up of, you see that top right image, a bunch of stack of these different 2D layers. And you'll see a lot of times like 1T or 2T or 2H or whatever different types of phases of the same compound. This is usually just their different stacking arrangements of those layers. But they don't really talk about that too much in these papers, but if you see that when you're reading other things, that's what they are. So a lot of these materials are hexagonal in planes. You're looking down on top of it, a bunch of hexagons, which looks awfully similar to graphene, which is great because you can match them up when you epitaxially grow them. So they have very similar lattice constants, and I talk about that a lot in both the WSe2 paper and the gallium nitride paper.
Is epitaxial growth you're matching the lattice structure of the substrate when you're growing stuff? Okay.
So that's the third slide I have, which we can just go
Oh, okay,
jump around and look at that too.
And in the paper that we read, I think it also matches the plane. So if there's a certain plane that's like
Oh,
available on the
yeah.
surface, it grows on
Okay.
that same plane.
Yeah, because I just wanted to like confirm that, because I tried to learn that on my own, but.
So when you're looking at, oh, I want to grow this material, what substrate am I going to use? You want to look at the A lattice constant a lot. So the in-plane lattice constant is what a lot of these are talking about. When I mention the thermal expansion coefficient, it's of the A lattice, as in A, B, C, the in-plane. So yeah, epitaxy is crystals growing on top of crystals in a very loosely defined way. So it's growing crystals in a preferred orientation on top of another crystal. So we were watching that video briefly, and they're growing it on top of sapphire. And so some ordered thing on top of another ordered thing. But van der Waals epitaxy is different. I think it's kind of the lower left image where there's this kind of space. Okay. So there's the space in between.
What happened? I
I
don't
just zoomed in.
No, he was excited.
Oh. It's like,
So yeah, there's the space where there's a van der Waals bond happening here instead of.
oh, that should be so fun.
So the second.
Yeah, they
picture
call van der Waals
Yeah.
force, but bond, but it's not a bond. It's just forces.
Sure.
What's
Yeah.
the nature of these forces, like compared to like?
Electrostatic.
Just
Yeah.
regular.
Okay.
old-
The regular electrostatic forces.
So, but van der Waals bonds are not as strong as a covalent bond or whatever. I'm just using that as an example. But so therefore, there isn't as much stress or strain that can be imposed on this material when it grows, because this bond isn't quite as strong. So the in-plane bonds are much stronger. Let's see. And not to get super confusing, but this other image to the right, the remote epitaxy, that's all what the gallium nitride paper is about too. So very similar concepts.
Yeah.
Let's see, did I miss anything? So with the van der Waals epitaxy, you don't care about the lattice mismatch as much, if at all, because those bonds with the substrate just aren't as strong because they're van der Waals bonds. So this, you see the matched, strained, and the relaxed. You don't get that anymore because there's this van der Waals bonding happening. So a lot of this paper is, hey, we see it's not strained, yay. And same with the gallium nitride one too. Let's see. So
I have a question
yeah.
before. I don't know, maybe it's a dumb question. I was thinking, so when we are doing the epitaxy, right, and we have the substrate, and we are not doing van der Waals, so we have a bond between the substrate and the new field that we are doing, right?
Yep.
And we measure properties. We're not measuring properties of use the new material we are ground. We are measuring properties also with the substrate, right?
It depends on your technique. If you're doing like a surface technique, like XPS, you're just going to see that top however many nanometers or whatever of your epitaxial film. But yeah, if you're doing Raman or something, you're going to see something deeper and you get the substrate too. So you
Right.
better make sure your substrate is different enough characterization than your film, so you have some sort of way of telling them apart.
So it's like there's TEM, and you can see the underlying silicon carbide for that one paper. Yeah.
Yeah. Mm-hmm. Like when I do Raman on my NBE grown films, I always get a sapphire peak or whatever. So
Yeah.
it's just.
And I think that depends on like the interactions between like the elements of the material that makes the film you're growing. So I think that paper with the gallium nitride, because gallium and nitrogen have like a 7 nanometer interaction kind of sphere, and the films that are being grown are like less than that. There is like an interaction with the silicon, basically, the silicon carbide, and so you could see that for that
Yeah.
reason.
So you can see like the charge effects from the underlying substrate,
Exactly.
and the
Yeah.
graphene's just thin enough
It's like polarity
that
even
you
like
can see it. So
creates a part in that because of
it
that.
just completely it doesn't screen it completely. Whereas you can still have buffer layers that are thick enough that it screens the substrate enough that you can't really see an effects from it. which you may want, you may not want. It's application.
Is this paper mostly off of like epitaxial growth?
Mm-hmm.
You know, I read my first epitaxial growth with the gallium nitride, and I like it a lot, so I might pick that paper up.
That's the one that
That's
you.
so funny. I crossed out both of these epitaxial papers.
They're not that deep to learn, so I
Okay.
would recommend them. So
You
there's
would
not-
or would not?
I would.
You would,
Because,
okay.
I mean,
Shit.
it's just kind of, it's thermo and it's some kinetic stuff, but it's very well explained in those two papers.
It's probably gonna be some lattice, like
And-
crystals
structure,
crystals and stuff,
but
yeah.
basic, like
Yeah.
like lattice constant mismatch
That
stuff.
one guy who said that Professor Liu, his advisor, he was like, I don't think he put up a paper, and I was like, he's a core class
Yeah,
professor. I feel like he
there could be some-
definitely put up a paper, but
Yeah.
I didn't want to.
Yeah,
question
this
it.
WSe2 paper is definitely my advisor, Dr. Vogel, because his first postdoc wrote it, and like I mentioned it to him, and he
Oh.
was like, "Oh,
Yeah.
that's nice." Like, yeah, and this is pretty much exactly what I do, and I've already read this paper. Like, it's been recommended to me to like, base
OT.
my own experiments off of. So
Yeah.
I'm 99% sure. But
Okay,
yeah,
so you're the pro in this paper. That's good.
yeah, hopefully. So the
You're
method.
not. Who is
I'm
it?
not sure. Bonnie probably knows a good bit about this too.
That's
So
a good point.
she also does some Indian cell. So methods of the paper a little bit, just touching. I don't really go into any of the instruments that these characterize, but the method is kind of unique to all the other papers. So molecular beam epitaxy, which is what I work on primarily, is a big, huge vacuum chamber, and you have these sources that are on the outside, and they heat up and create this molecular beam of source material that is then deposited on a heated substrate. So, let's see if I hit all my bullet points. So, the ultra high vacuum is a much cleaner environment than like ALD or CVD. You don't have any of these other gas carriers sending something to a substrate. It is directly just the pure source material. It's as pure as your sources are. You're down to like 10 to the minus 9 torr or so, which is a couple orders of magnitude up of like just space. It's very low vacuum, very expensive. So the mean free path of your molecule or atoms, whatever you want to call them, traveling to the surface is longer than that distance from the source to your substrate, so they don't collide with each other and form compounds, theoretically. Selenium chalcogens are a bit sticky and just can form larger compounds, but
Does they collide mid-air and form compounds?
I think it's when they're already evaporating off, they just form that.
Ah, okay.
But they don't really mention that in the papers as much. It can affect how it is sticking to the surface though, like the sticking coefficient.
Is the mean free path something that you could alter?
Yeah, so if it's a higher pressure in the chamber, then it's not, your atoms aren't gonna travel as far before they hit something else.
So it's like low vacuum is why, okay.
Yeah, the big deal about molecular beam epitaxy is that it's at ultra high vacuum.
Or high vacuum, sorry. Low pressure.
Yeah.
So
So the,
that would be a good idea to look at like the mean free path equation if you haven't seen it, just to like make sure you know what that looks like.
and just like Google molecular regime, because there's like normal air that we exist in and stuff, and then things act very differently in the molecular regime, where you can just throw an atom and it keeps going, which is why this even works. So it's very directed molecular beams, so you don't have a ton of waste either, and things will go where you stick them, basically. And another thing with the MBE is you have these shutters in front of your sources, which is just like a sheet of metal in front of it. And you can control when you turn on and off these different molecular beams with that. You just flip a switch. So you can control when you're putting the flux onto the substrate, and you can control how much flux by how much you heat up these effusion cells, these evaporation sources. I'm using lots of fancy words.
Do
Okay.
you have like a quartz crystal to measure thickness, or you're just like, I left the shutter open
We
for X amount
have
of
a
time?
pressure gauge, an ion gauge.
The one that's not working, right?
It works nice.
Oh, okay.
Yeah, we're good.
Okay.
We have a pressure gauge, so when we are measuring how much flux comes out of these sources, we are measuring the pressure, and those are directly related. So you'll see sometimes something called beam equivalent pressure in MBE
Okay.
papers, or BEP. And that is something they're measuring with a pressure gauge to try and determine how much flux you're throwing at your substrate. So that's how many atoms per centimeter squared per second. And that is, so flux,
Okay.
how much stuff is in the substrate.
Yeah, I have a couple of questions.
Mhm.
So, you mentioned the material is deposited on like a hot substrate.
Yeah.
Why is the substrate put at the high temperature for it?
So that can affect how the material that hits the substrate diffuses around. So if it has more energy, it'll diffuse around more. Or it can also re-evaporate off the substrate.
Okay.
So I'll go a bit more into that, like what they did in the paper
Okay.
related to that.
Okay.
So, and right now too. So like my typical MBE recipe, I'm looking at what is my substrate. And in this paper, they talked about the bismuth selenide, HOPG, the highly oriented pyrolytic graphite. They also talk about silicon carbide and the gallium nitride. And there's also C-plane sapphire. All of these can be substrates. And they use these because some are conductive, some aren't, some have this nice hexagonal lattice, like HOPG and silicon carbide. Sapphire is a nice insulator. It might just be easily available and cheap. So that's kind of why they use those. And so another thing I'm looking at in my recipe is the substrate temperature. How much do I want my atoms to be moving around on the surface? How much energy am I imparting on them before they crystallize? And when the atom hits, is it going to want to just re-evaporate off, or is it going to want to stick there? And then I'm also looking at the flux of my sources. And I'm usually looking at a ratio between my metal and my chalcogen and comparing those. And it's not gonna be stoichiometric. I'm not gonna have one tungsten atom
To
to two selenium atoms necessarily.
okay.
It'd be nice if it was, but then we have the added substrate temperature. So selenium has a lower vapor pressure.
It's in here.
Um,
I don't.
Okay.
Why would I know that?
We took the thin films class.
Yeah, but they're not gonna tell you the
That's
solution
true.
has a vapor pressure.
Usually
They say it in here. I remember
Okay.
them talking about it.
But they want us to evaporate off more than the tungsten would. So,
Oh, so
At a
you have,
certain
like,
temperature.
vacancies.
or you just over deposit selenium
Mm.
and you're fine because you have an excess of it. Some of it's going to evaporate off, enough of it is going to stick.
Okay.
But it can create defects if you do too much or change your phase or something weird like that.
If it's like non-stoichiometric and you have like more evaporating onto it than the other material, like couldn't it just form like areas where it's higher in concentration, where there's like maybe less tungsten, for example?
So that's the great part about molecular beam epitaxy is it's so uniform because it's at such a high vacuum. You don't really get as much of these pockets, and if you do get pockets, it's with the metal. We want to stick to itself
Okay.
with metallic bonding.
I got it. Okay, the
Sweet.
the chalcogen sticking coefficient is much lower than the transition metal due to the short mean-free half-life time. And
Metal wants to stick.
so it wants to stick.
Metal wants
No,
to stick.
the metal wants to stick. The chalcogen
The
does not.
chalcogen does not want to stick. It wants to evaporate back off. Yes.
So you deposit more of the chalcogen
More chalcogen.
to account for the.
Mhm. And that's a very common thing with any of these TMDs.
-9 millibar for tungsten and
Vapor
negative-
pressure?
Yeah.
Okay.
-7
Okay.
for selenium.
So it has a higher vapor pressure.
So it's a higher rate,
Okay.
more of it.
It wants to evaporate off at a certain temperature, which is controlled by your substrate temperature. And that's why you want that temperature control in your substrate, is so you can determine how much, or at least these general trends and how much you're evaporating back off. and these are all just thermocouples you set. It's not, there's not much more to it than that. Yeah, I think they mentioned a Reed electron gun in this paper too, and that's just, it's an electron beam that's hitting the surface and deflecting back off, and it tells you how rough the surface is. And you can use that to tell, okay, we have one 2D layer, and it's rough again. Then it has another signal that's flat. Okay, we grew another 2D layer. So you can count how many layers you have and therefore thickness with those. Let's see, did I miss anything? Yeah. So what's your substrate? What's your substrate temperature? What's your flux of your sources? These are your 3 big things you want to pay attention to in MD. I already talked about epitaxy. So, okay, so kind of broad overview of the paper once again. So the problem was they have this high nucleation density. So they have lots of little spots on the substrate where you're starting crystal growth. And this makes for a lot of grain boundaries. Because you have lots of little sites competing with each other, and oh no, I ran into my neighbor, I must form a grain boundary, but I'm like super small, I can't go anywhere. And that is not good for electronics, because your electron is trying to move fast and hits grain boundary, it can't go anywhere, or hits something and it has to go over some sort of boundary, very bad. So you have low carrier mobility. So they want 2D growth, and they use a 2D van der Waals material model, where they go a very long paragraph of why 3D growth is bad for 2D materials. Who would have figured? Because it overestimates atom plane interactions. So they try and understand the kinetics and thermodynamics of the system. So they kind of spend a little bit on the different growth modes. So I found a little picture on the right there that says, so A is the, I'm going to butcher the names, Frank van der Meer 2D growth, and that's the one you want, so it's layer by layer growth. And B is the Vollmer-Weber growth, which is 3D growth, bad in this case. And C is the Stransky-Krastenov growth mode, which is a combination where it starts out as 2D but then becomes 3D, which is also bad. So those names will show up a lot in epitaxy papers, but that's all they need. It's just what the type of growth is. So as a result, in the paper they played with the flux and the substrate temperature to affect these different, see what happens with these different type of growth modes, and they were able to figure out we want low metal flux, high substrate temperature, and a lot of chalcogen. So the metal flux, the amount of metal you're throwing at the substrate, is kind of your deposition rate, because it's what the chalcogen is going to stick to, and it's heavy and wants to stick. The high substrate temperature makes sure there isn't, everything's still even, everything is allowed to diffuse and form these larger grains, and you're just imparting more energy to your material. And we want, like we discussed earlier, the chalcogen-rich environment so that we don't have too much re-evaporating off with our high substrate temperature.
So the higher substrate temperature kind of allows for diffusion, so things can be like homogeneous and stuff.
Yep. So there, it talks about, these different energy barriers to overcome different, like the edge, getting over the edge. So they wanted to overcome these different barriers, give enough energy to overcome the different barriers in order to form this 2D growth. Which it explains these pretty well, I feel like, in the paper. But yeah, the general gist of it is you want to make sure your atoms stick enough to the substrate and form not too many nuclei, but still hit the substrate and form some. And so that depends on the substrate lattice, substrate temperature, and the flux. And then once you do get on the surface, how are they going to stick around and how are they going to move? So how is each new layer formed? You need to overcome these different energy barriers, like getting over the edge and forming these nice 2D layers as opposed to just stacking on top of itself and making the 3D layers.
Is that like slow but less nucleation sites the reason for the low metal flux? Or
I don't know if I'd use the word slow, but just like less metal, I guess. So there isn't, but it has to do a lot with the metal deposition, so it doesn't try and pile on top of itself or like too closely packed together and make all these nuclei
okay.
and start growing all these grains everywhere. You're trying to interrupt the metal bonding to itself enough to form the crystal structure you want. So, like, I had a problem with my experiments where I just see a whole bunch of metal blobs everywhere.
Mm-hmm.
Oh no, I need to add more like selenium and interrupt the growth of the blobs. So,
Do they go into like homogeneous and heterogeneous nucleation growth types, or no?
in what way?
Like in the paper, or is it like? Do you think that that being asked as a question would relate to this paper? Because someone in my lab mentioned, she was like, "Oh, I remember like in one of the papers she took the exam 2 years ago, and she said she remembers having a question where like one of the papers asked like, okay, we talked about nucleation now, like in the thing it was like describe the 2 types of nucleation growth."
Okay. Well, this one deals a lot with nucleation. Gallium nitride one does not as much.
Yeah, it's weird. They're trying to explain it, but then they didn't really mention it too much.
Yeah, this one is kind of like, okay, nucleation happens, not necessarily the type of it.
Okay.
Because I think there really only is this one type of nucleation in this paper, but it wouldn't hurt to look that up for sure. These 2 papers are very much like, what type of epitaxy is it? Like, how am I interacting with the substrate? Not necessarily how am I forming different nuclei.
Okay.
You have a question there about whether the atoms stick to the substrate and form a nucleus or diffuse along the surface. Which do we want?
So you initially want nucleation in the first few stages of growth. You want enough nuclei in order to make some sort of film. But predominantly you want it to diffuse across the surface, and that's why they use the higher surface substrate temperature.
Okay.
So, yeah, you want this self-diffusion. You want to give it enough energy to be able to move around and not form 3D islands and 3D layers. It's really this whole balancing act of, we want material, we want it to be flat.
Does each material have its own self-diffusion energy, or is that something that you fish for?
It's kind of based on the weight and the size of the atom, they're called, which is the atomic species once it has impinged on the surface. It's participating in that epitaxy. Like the selenium can try and bunch up together, the metal can try and bunch up together. There's a lot of different factors, and they just kind of lump it under like surface diffusion.
Okay.
Yeah.
So when you're talking about the self-diffusion, you're talking about the final step in this energetic diagram, like or the add atoms, or both, because
I think both.
Oh, okay.
Yeah, because there's diffusing to its proper, like, just when it initially hits, and then when it gets to its spot. Like there's it has to overcome, first getting out of the gas, then staying on the substrate, then getting over the edge, which is the 2D growth, so it's not stacking and forming.
Oh, we can understand these Q subs. No, I think it's Q substrate or something. That energy of that.
Yeah.
Oh, you understand that. So
So that's moving to its spot.
okay, so at the beginning, when we want to absorb, the energy to the absorbed atom is the E80, right?
I think so.
The whole thing.
Yeah.
But then we have this energy of the substrate. I think it's some energy barrier due to the substrate, right?
This
And
is
then
Well, diffusion on the substrate.
Yeah, I think it's the barrier to diffusion
to diffusion
happening
on
where
the
you
sub-
want it to.
Oh,
Yeah.
okay. Now,
And then sometimes it's got to get over this edge too, I believe.
okay. And now we need to overcome the energy barrier due to the age.
To form
Okay.
the 2D layers.
To the layers. Okay.
And then the last one, I'm a little confused about. I think that might be the re-evaporation or it just becoming part of the flake, like it not becoming another nucleus, basically.
Okay.
Um,
Yeah, because there is a Q of vacuum too.
yeah,
right?
I'm not quite sure what
What is that?
that means in this case.
Yeah.
Because they have all these breaks in the graph too, so it's
Yeah.
very much like non-committal on how much energy these are. But
Okay.
it should tell you in the papers.
And vacuum is over the like the surface, you know, when all the materials is complete, there is vacuum, right? What does mean? In the
Maybe
figure.
that it just doesn't belong to that
To that, okay.
area, that nucleus anymore.
Wait, in the flake?
But yeah, I'm not quite sure what
Mm-hmm.
Are they saying that there's movement within the flake even after it's formed?
there shouldn't be. But
Well, it should be. I mean, you're gonna have diffusion within the flake. It's just not leaving the flake.
I don't.
Everything's
I wouldn't call
moving.
that. Yeah, but that's not part of the epitaxy process.
Right.
necessarily.
Very true. Yeah. I mean, maybe
Um,
that's what it's saying. Like, it's not part of the epitaxy. It's just the internal movement.
Maybe. Yeah. Of
Um,
it not forming defects or dislocations or something. So, yeah.
So all that graph is about like diffusion and energy, basically.
It's all like
The
gives
epitaxial
energy,
wall.
kind of type of reaction barriers, that sort of thing. That is how this is modeled a lot.
And the reaction coordinate is just how far it is in the reaction
I think
process
so.
that you want.
Mhm.
Yeah.
I'm not a huge
Towards a
fan of
finished
this
project.
plot, to be honest. It's a little confusing.
Yeah, it's a little confusing. Yeah. The inflate one, I don't understand.
Yeah. Because kind of its final state should be okay. I'm a nice crystallized thing where I want to be. I'm a nice 2D flake.
it does not explain
Okay.
the figure in the paper.
But it's still heated though, right?
Yes.
So then even if while it's heated, diffusion's still more likely to occur.
Yeah, that's true. But also once it's locked into its crystal structure, it's gonna want to stay there, and it gets covered up by other stuff on top of it too.
I'm seeing like it's QVAC, so maybe it's like on the very surface, whatever atoms are on the surface might
And it
leave.
re-evaporates or
Yeah.
something. That's my best guess too.
So it's like in the flake form, but the stuff on the very surface of that flake.
Yeah, because you can have, like if you were to stop depositing for whatever reason, your selenium or whatever, you can have it evaporate back off and
But it's
cause
weird
problems.
because at least Q edge and QVAC should be happening at the same time.
A lot of these should be happening simultaneously, and that's why I don't like this
Yeah.
plot. There's a lot of this. That's why I kind of like the picture version over that I have in the top right there. That one's not perfect because it has some weird, like interdiffusion with the substrate stuff happening or lattice incorporation, which may or may not be happening. But it shows everything happening simultaneously, and I like that a lot better. And it shows what's happening on the substrate a bit better.
This is from the paper too, that thing?
No,
Oh, it's
it's just
another
something I googled.
Okay.
Sorry, bad presentation. I didn't cite my sources, but
No, you're good.
I have a question. So which is the main advantage to use molecular beam epitaxy instead of, I don't know, a different stuff?
CBD or something.
CBD, yeah.
It's clean. You don't have those other reactions happening. This is
Okay.
purely physical deposition, not a chemical reaction happening.
And can you,
Okay.
and can you get the properties from the underlying layer with like CBD?
Sure. That's more of a thickness of your film related thing, not necessarily how it's hitting the substrate.
You'll have more impurities with CBD.
Yeah,
There's
and,
other
and,
atoms
and that's
running
that's my question, because even if we know like a 2D material as a definition is a material without dangling bones, we know that we can have defects, and if we have a defect, we have dangling bones, right? That's why we are using this MBA, like the molecular beam, because we avoid defects, we avoid impurities, we avoid defects,
Yeah.
so we avoid dangling bones. My
It's
2D
very
material is
clean, good crystal
pure.
quality.
Like even the
okay.
graphene paper had defects, so.
The gallium nitride one is MOCVD,
Oh.
so
So
metal,
you-
metal organic.
Yeah.
Okay.
And I can go into that. But, just to finish up this paper, so yeah, the two plots they had in there kind of showing the general trends. This is with the model they used. So they showed that there's more nuclei with more absorbed atoms. This is all just saying the same thing we've been saying. There's less nuclei with higher substrate temperature and more nuclei with more flux. Checks out. You throw more stuff at the substrate, you have more stuff on it. Wow. You heat it up, more stuff evaporates off. Who would have thought? They use a lot of fancy words for pretty simple stuff, so,
Yeah.
they're not too complicated. But their general thing was they're showing that the nuclei density depends on the flux and substrate temperature.
So this is like the results now. Okay.
Sort of. It's more of, I tried to look at their model a little bit, because that's not a super, necessarily intuitive thing. But you really just need to look at the general trends, and it's pretty good in the descriptions of the plots of what they are.
Wait, are these models or are these like experimental?
This is models
Ah, okay, that makes
of their
sense.
absorption rate.
All right.
So, hitting and sticking to the substrate, as opposed to like, I'm usually looking at like AFM actual pictures of my substrate and what it looks like, but they did both. So they have this model and they have pictures as well, which I didn't really put in this because I feel like they're pretty explained well on paper.
So I have a question. I'm sorry,
No,
because
no.
this is the first time to see
No,
that kind of plot for me. We want good absorption rate and good nuclei density, right?
You want moderate nuclei density. You don't want a ton of nuclei, or else you're going to get a super grain, like a bunch of grains, and you don't want that. You get the super high nucleation rate, which is the whole problem to begin with.
Okay.
So you want low nucleation rate in order to have larger grains.
So it looks like that.
Nucleation rate. So that means the nuclei
Or
density.
density.
Okay.
Same.
Okay,
Doesn't
the same
mean
thing.
growth rate.
Yeah.
Okay.
So like the
okay.
green plot is like mid.
Because absorption rate is different.
Yeah.
Okay.
But you would probably want to go as low of a nucleation density as possible,
Mm-hmm.
with still having something on the substrate.
Okay.
So, you would want, what is it, blue?
Yeah, dark blue.
Yeah.
But that has a lower temperature, and that's substrate temperature, I'm assuming?
That is,
The blue one
the
is lower.
absorption rate.
The
Is-
blue
Wait, we're
versus
looking at
the
the
red
left.
versus the
Yeah.
yellow?
I was
So the
looking
blue-
at the
So this is the left graph, has nothing to do with temperature.
Oh, I was looking at the right
Oh,
graph.
Okay.
okay. Do we
Because
wanna
that's
do-
saturation, nuclear density.
wanna
and
look at that
absorption
one?
rate.
Okay.
Yeah.
Right graph has to do, yeah. So that one is showing, with less nuclei with a higher substrate temperature.
That makes
Exactly.
sense. So it's like harder for nuclei to start forming when the temperature is higher. It's like because
Because it's evaporating off.
yeah.
Okay.
It's
I was thinking,
showing-
why it is nuclei if it is evaporating?
It's showing a higher absorption rate for the same saturated nuclear density. Like if you look at 500 versus
Okay.
300,
Yeah.
they have the same nuclear density at close to zero,
Close to zero, yeah.
but
Because
with a
you're-
higher absorption rate.
Yeah, as you increase the absorption rate, then you get these differences, I guess. Let's see. There's less nuclei with a higher substrate temperature. Those are their
So that means the nucleation density is lower, right? But
both,
the
yeah.
absorption is
It's
higher.
higher, so you'll have higher
Okay.
growth, faster growth, right?
Fa-
You're throwing more stuff
Oh, I see what's
at the
happening.
substrate.
So if you're at 300 and at 0 and 1, 0 nuclear density and 1
Mhm.
absorption rate, nothing's gonna happen.
Mhm.
But if you're at 0 nuclear density and 100 absorption rate with
Mhm.
500,
Yeah.
you're gonna get
Okay.
not a lot of crystals, fast growth.
Yeah.
Right?
So you have so at higher temperatures you have like less nuclei forming, but a lot of like single, I guess, atoms on the surface kind of running around.
It takes more stuff to make it grow
Okay.
when you're at a higher substrate temperature because it wants to re-evaporate off. Yeah, so you need more flux. I think that's why these start at different points. Okay. So that is their model.
So wait, the absorption rate is differing just by the temperature that they have, not by the flux. They're not changing the flux at all in here, right?
Absorption rate could kind of be your flux.
It might not be the output of flux by the
No.
system, but it'll be the
Trends
absorbed.
wise.
Oh, so it'll be the absorbed. Like it's not necessarily. Is it necessarily atoms?
Sorry,
Hello.
I thought they had this book room blocked off.
No, they didn't.
I'm sorry.
Do we need to leave?
No, it's on my work order. I'll wait the next weekend.
Okay.
We'll get it.
Thanks.
Will y'all be here next week?
Not in this room.
We don't
cannot
need to
be in
be,
this room.
yeah.
Yeah.
Okay.
We'll go
Okay.
home and, eat dinner.
Okay, I'm sorry. I thought they blocked it off because it's on my work order.
You're all good.
No, it's okay.
I'm moving this stuff out.
Sorry, thank you.
Okay, so adsorption rate isn't necessarily add atoms.
It would be that.
Okay.
So it's absorption.
So you have a lot more add more
Yeah.
add atoms. Okay.
More stuff is sticking to the substrate and doing what it's supposed to.
You might have the same number of atoms in the system, but you have more atoms absorbed onto your thing.
Okay.
Yeah.
Yeah, that's exactly what I thought. Cool.
Participating in that.
And which is the difference like with a nucleation point? Because a nucleation point is also absorb atoms, right?
Yeah, but nucleation is, okay, you have a new grain happening here.
Okay.
So not every atom is gonna start a new
In the-
nucleation site.
You guys
Oh,
ever
okay.
see those little sugar sticks with all the crystals on it?
Yeah, I think.
You know what I'm talking
Did
about?
I
Oh
make them?
yeah,
Little
the
one
rocks.
and
You make
the-
them,
Put a
yeah.
string
Yeah,
in
yeah,
a
yeah.
thing of sugar water,
Yes.
and then the crystals will grow.
Yeah.
So that's really polycrystalline, right? You have lots of nucleation points. So imagine if you had that, but it was only one nucleation point. It would just be a clear block, like you see a quartz crystal.
Mm-hmm.
That's like one
Yeah.
clear,
Mhm.
long. I mean, that's not single
Same.
crystalline, but
Same thing, same
Yeah, the same
concept,
thing,
yeah.
yeah.
Mm-hmm.
You just have one nucleus. Wow, that's crazy. Okay.
Where does the nucleation site happen on the, on the surface, like in the middle?
It's pretty random.
Okay.
It turns out to be. There's definitely like surface treatments people do to make it happen in certain orientations, and like you can cut a step edge or something on your substrate.
Okay.
But it's not just like one, like once you've already made a film or like made a surface and then you're like about to, I guess, grow a new one. Is it like one forms and then, or is it like a couple form and they all merge together to then create your new like layer?
It can be either.
Okay.
So like in the gallium nitride paper, they had a bunch of them that didn't really ever form coalesced foam or anything.
Mhm.
That can happen too, but they're a lot bigger.
Mm.
It really, depends on what you're looking for.
So
But it can be both. In this case, in this paper, the like heavy, dense nucleation density, there's a bunch of little spots happening everywhere, and then they all run into each other. Not good.
This
Mm.
paper, this is all a bunch of different grains.
Oh
So
yeah.
there's all these
Yeah.
nucleations.
Okay,
Mhm.
okay.
So imagine it being one
Yeah.
thing, no
Yeah.
grain boundaries.
Yeah. That's what they want though.
That's
Yeah,
what we
that's what they
want.
want.
Yeah.
So
That's
Not
not, did they
entirely
necessarily
possible.
get?
But you want them as big as possible.
Yeah,
So
okay.
you want the fewest number of nucleation sites.
So is it that you have a bunch of like add atoms like ready to rumble, and then one site nucleates, and it kind of just like triggers all of them to kind of form together? Or?
They nucleate as it hits the substrate, really.
Okay.
So there might be, I don't know, it's really random. Because like one or two will clump together and start a nucleus. And then a whole bunch of other guys will come and join that guy. Or maybe another nucleus. And, they just stay there. So that can kind of help with the surface diffusion thought too, is because if it's hotter, they're not going to want to form a nucleus over here. It's going to be hot enough that I have enough energy to go and join the other nucleus.
Mhm.
So.
So now they're gonna work with a higher substrate because then they get less nucleation sites.
Yes.
Okay. But you also want, regardless, like if you have a low nucleation site, you also still want low nucleation density, or moderate
Same.
nucleation density.
I think you're saying. the same
Nucleation
thing.
density and nucleation sites are the same thing.
Yes.
Nucleation density is number of nucleation sites per an area.
Okay, I thought it was like the size. Okay.
The size is
That
gonna
makes it
change
better 'cause it's
after
just like-
growth rate.
Okay.
So
I have more questions. I have more questions that I'll ask afterwards.
it's good. Like a lot of this is just definitions, and then the concepts are really simple.
Yeah, I'm saying we probably haven't even gotten to like the results.
I don't know, this is a pretty
I'm-
good overview of
Yeah,
everything.
I'm pretty. Yeah, this is kind of
No,
the
this
end
is
of it,
awesome.
honestly. So like just some questions I kind of came up with or thought about were like just know the growth modes that talks about. That's the major point of the paper.
Right.
Is why it's 2D growth and why we want that. And then so just knowing Vogel. He really likes his practical questions. So like if something happens, what's going to happen with the growth conditions? You know, different scenarios really. And he also likes his first principles stuff. So what are the underlying mechanisms of the process? he was a big like fan of making like just the core courses very much like, okay, we have kinetics class, we have a thermo class, like that sort of thing. He is an electrical engineer, but I don't think that's really relevant to this paper.
Thank God.
But he does like a lot of electrical stuff. That's his thing. But yeah, for sure kinetic stuff, review thermo. He's a lot of meetings he asks like, oh, is this a kinetics like mechanism or is this a thermodynamic mechanism?
That's important.
So
yeah.
like, in my understanding, the substrate being hotter, that's a kinetics thing, right? Whereas the thermodynamics, that
He
would
does
be.
energy barriers.
To
Something
nucleation
that
or
happens.
something.
Sometimes it can be both.
Yeah,
Yeah.
can be
Right.
both actually,
Mhm.
because it's also related with the energy diagram
just,
that they
like,
show.
Make a good
And in
case.
that energy
Yeah.
diagram, you have both.
Right, but I'm just thinking like, so thermodynamics is you hit the substrate and that's what you are in that point whenever you hit the substrate. Whereas
yeah.
kinetics, time
Well-
happens and things change.
Thermodynamics would be like re-evaporating off the surface or
Yes.
something like that. Kinetics would mean the surface diffusion of
Diffusion.
I'm gonna hit an energy barrier if I try and go
Mhm.
over this edge, so I'm gonna stay put and make 3D growth or
So,
something like
so
that.
then what would that initial nucleation be?
Like for hotter substrate or what?
Like I guess like the hotter heated substrates that they have.
So that would mean that it would want to form less nuclei is with a hotter substrate because it's gonna wanna coalesce into the nuclei that already exist because it can diffuse on around the surface more.
I'm saying like is nucleation thermo and kinetics like combined sort of or okay.
Yes, so there's different effects from both.
Mm.
And sometimes you can, if you're looking at an overarching kind of explanation like what I just gave, you have both in there. Because temperature is going to affect how much it can move around, because it imparts energy. So just trying to separate, maybe not even separate, but think through the whole process in your head. There are both things moving around and things caused by energy and heat.
So you're saying the kinetics is like the movement,
Yes.
and then the thermo is like energy and heat.
Yeah.
Okay.
Yeah. And to me, it's like sometimes thermo is more like, is this possible or not?
Yeah.
And
Yeah,
kinetics
that's-
is like,
Do I?
how
How
fast
fast,
or how
exactly.
fast is it gonna
Yes.
happen? Is it gonna happen? Is it not gonna happen?
Yeah, so there could be like oh, is this gonna happen thermodynamically, or is this gonna happen with kinetics kind of thing?
Yeah.
What's the main mechanism happening?
Cool.
Yeah. So.
Like graphite and diamond.
Oh, that was it?
That was good.
That was
Great.
awesome.
Yeah,
Okay,
that was
yeah.
great.
I think I could like read this paper and understand this.
Yeah.
Now.
It's
And
pretty
please
good
share,
paper.
share the slides, everyone.
Yeah.
Yeah,
this-
Yes.
let's
Oh,
put it
yeah.
on
For sure,
Discord.
for
That's
sure.
where it's
Yeah,
from.
yeah.
Wow, 47 minutes.
Yeah, let's stop it.